I think the translation of this to the treating diseases has just been the most amazing thing. I can honestly say when I went to the NIH to study the basal ganglia, I had no intent of curing any disease. I didn't know what disease to even cure. Okay. So the question you asked me earlier on about key people, I was going to extend it to key animals or key models, and by all means, the introduction of the MPTP treated primate was a door opened to understanding, I think, the basal ganglia and Parkinson's disease. And when we saw that, we just shifted immediately to begin studying that.
Welcome to Stimulating Brains.
Hello and welcome back to Stimulating Brains, episode number 22. This conversation I had with Mahlon DeLong is surely a key highlight of this podcast. Mahlon has been and still is one of the key important figures in the field of neuromodulation and has been instrumental in paving the way towards detailed models of the basal ganglia and how they interact with cortex and thalamus. Mahlon DeLong studied at Stanford and Harvard, then did his internship in Boston, spent 5 years at the NIH for research, and continued residency at Johns Hopkins later on, where he then became an assistant, then associate, and then full professor. In 1989, he was recruited to Emory as chair of the Department of Neurology, which he did until 2003, and then became the interim director of the Comprehensive Neuroscience Center. He's the co-director and founder of NTICE, the Emory Neuromodulation and Technology Innovation Center, whose goals are to foster advancement of neuromodulation and the development of innovative neuromodulation technologies for the treatment of neurological and psychiatric disorders. Dr. DeLong's most recent award is the 2014 Breakthrough Prize in Life Sciences. He was cited for his work defining the interlocking circuits in the brain that malfunction in Parkinson's disease. This scientific foundation underlies the circuit-based treatment of Parkinson's disease by deep brain stimulation. We have some guest questions by Marwan, Hariz and Hagai Bergman, to whom I want to express my deepest gratitude. I also want to express deep gratitude to Patricio Riva-Possi, who introduced me to Mahlon DeLong, explicitly facilitating this podcast episode. Thanks a lot, Patricio. And I hope you all have as much fun listening to this exciting conversation I had with Mahlon DeLong. Episode number 22. Welcome back, Stimulating Brains. So, Mahlon, thank you so much one more time for taking part in this. And by now I will have introduced you more formally. So we can directly start with questions. And to break the ice, before we get into science or medicine, I usually ask about hobbies. So what do you do when not involved in medicine?
That's an interesting question. Well, I retired formally, I guess, about 5 years ago, or 4 or 5 years ago, and cut back. COVID struck, and everything converged. So I'm filling time somewhat vicariously, in the sense that we had planned a lot of trips, my wife and I. Yep. Those didn't happen, of course, and we're just starting again. But we've tried to do virtual cruising, I guess, on the television, and really quite a lot out to see out there. That's been interesting, especially going sometimes back to places you've been, and that's been a fun part. I read a lot. I read incessant. as much time as I can find. I'm very into. I started in physics and astrophysics. Actually, that was my passion when I started undergraduate. But I ended up in history because of some stimulating courses and interactions, opening up a new world. And so I read a lot of history. I'm very interested in particularly ancient history, what happened before societies were formed, before agricultural, that early period. There's a wonderful book out. I just ran across the history of everything. It is an amazing recommendation for anybody who wants to follow.
Great to hear. Thanks.
Yeah. David Graeber is I think it's the #1 book on, this is not hidden or obscure recommendation, but it's fascinating.
Do you still play the alto sax? I read that you had a band in high school a long time ago.
Oh my God, where have you been? Where did you? Yeah, that was passion for middle and high school. We played swing band. It was a swing band, and that was. I still have the sax. I still play guitar and somewhat recorder and do those things, but not like I did before.
Right.
But that was a wonderful part of my life, actually.
And I heard 6 grandchildren. Is that still true? Or is it more? Yeah.
I think that's right. So, seven.
7. Wow.
Yeah. I was going to say, what do I do? It's fortunately 6 of the grandchildren live in Atlanta, so we have them every weekend, and through the week as well. So it's a remarkable thing.
That's amazing. I can imagine. Yeah, great. All right, let's dive into the topic though, science and medicine. Yeah. So you studied at Stanford and spent your junior year in Berlin. I had to ask, do you still speak a little German or Russian? I think you learned the 2 languages.
Yeah, I was going to be a diplomat. That was my goal, and I got a scholarship or exchange program at the Free University, Freiheit University. So that was a wonderful year. Did a lot of traveling, and at that point the wall was not up. Sorry, and we could go back and forth between East and West. And I traveled to Russia and Poland and got to see a bit of the world. I was thinking about history and also diplomatic service, and then something happened in my last year at Stanford. I'll tell you about. It's one of those aha moments.
Please do. Yeah, please do tell. What happened?
Well, I had come back and was getting interested in behavior and psychology, I guess you would say. And all my courses were hard science. I had never taken a life science course. So I took it because I had to graduate. And it was biology, sort of a basic course everybody took. And I saw on the screen cells dividing. And I thought, oh my God, the chromosomes. It was like this world, this life science. I didn't call it life science, but it just hit me like a bolt of lightning. Oh my God, this is what I want to do. It's something dealing with the brain. Brain came very quickly, but the initial was something about biology, I think, and understanding life.
Great. Amazing. So later you went to med school at Harvard and then also did your internship at, I think, Boston City Hospital. What were, in general in your career, crucial turning points, and who were the mentors that really stuck out, that influenced you most?
Well, I'll back up a little bit to Stanford. The person there who probably had more to do with that than anything, and as much as anybody, was Don Kennedy, who had come there he'd been to Harvard and Syracuse, I think. But he said, I talked to him and got to know him quite well. He was working on invertebrate nervous system and helped. I took a year as not a graduate student, but in a postdoctorate anyway, and spent a year with him setting up lab and doing experiments, if you want. And his advice to me was kind of shocking because I had planned to just stay there at Stanford. I knew a lot of the people and had gotten, underway. And he said, "Go east, young man, not go west." Great. And so I ended up at Harvard. I applied and they gave me a ticket to come. So I said, okay, I might as well. And that's how I got to Harvard. It was one of the best decisions. Well, I don't know. You never know what the alternatives are, but it was sure. Just at a time that Steve Kuffler had, for the first time, put together the neurosciences in a department. He didn't call it a department, but we called it neurobiology. It was the first grouping of anatomy, physiology, pharmacology, and all of and the imaging at the time. All of those pulled together in a department, and we had the most wonderful faculty. Frischpan and Potter, Nobel laureates, in their youth, who were teaching these courses. So it was a remarkable experience and a rich one for neuroscience. I may have taken us off track here a little bit, but
no, was exactly the question. So I read that you also got to be taught by Danny Brown at Harvard as an intern, and then also.
I can tell you. I'll tell you a short story. I had, after my freshman year, I was in anatomy in the second year, and I came down with a viral encephalitis. They thought I had myoclonus and I was really obtunded, and they decided I probably wasn't going to survive, and called the family. And Denny Brown came to see me during that time, and I'll never forget watching him, looking up at him. I didn't know who he was at that time. They just said, "The specialist is coming to look at you," and I heard him mutter myoclonus, which I didn't know what it was at the time. But it was a remarkable experience, because then I got to know him when I went to City Hospital. Not know him close, but anyway, I had exposure. One of the giants of basal ganglia research. Interest.
Great. And then other mentors that were important or turning points in your career that followed.
Yeah, well, certainly. When I went to the NIH, I have to say a turning point was the Vietnam War, because we all had to skedaddle and get a place where we could avoid the draft. We were the Yellow Berets, as they called us. But I applied to the NIH and visited and got, this is just, it was remarkable. And Ed Everts, who had just, was the top primate physiologist in behaving primates there was. I mean, he was on fire. He offered me the last position available in his lab. There were 3 or 4 who had just come on. So that was a huge turning point, and I'm eternally grateful to Ed. And he was a rather difficult fellow as a psychiatrist, and that's another whole topic. But he was very instrumental in everything.
So would you say you learned single cell recording in that 5 years at the NIH? Because I read you also looked at grasshoppers before that, even, right? Is that true?
Well, that was with Don. Don Kennedy. Yeah, that's right. Well, yeah,
the 5 years.
So Tom, really, I learned it from Tom Thatch, single cell recording and behaving primates. Tom he was working on the cerebellum, and we were very close, as the entire group was. There were half a dozen people there, and we learned from each other. Ed was on the scene, but not in the lab. And each of us, we had our own, it was incredible. We had our own lab and were responsible for doing everything. It was a great experience. I can name other people, but I think those are the key ones. Guy McCann at Hopkins, who was a tremendous father-like figure. I mean, he had just started the department there and had turned it into the greatest group of young people I think you could imagine. And that was a tremendous environment for everything that followed.
And I heard that was a golden era at the time.
Absolutely. Yeah. It was, as I mentioned to you, strangely, we got into the this is getting ahead of the story, but I got interested in the basal forebrain for a number of reasons. But we had identified those neurons in the work I did at NIH, the basalis neurons and their dispersal throughout the pallidum, and showed that was related. Those were lost in Alzheimer's, and so we followed that up with a lot of physiology. Rusty Richardson was the key person in that, looking for what that might be contributing.
So I think that one of the key achievements in your scientific career is, of course, the circuit model of the basal ganglia. So, and it is really hard for somebody like me that's younger now in science to even retrospectively learn how it emerged, what the story was at the time, what the knowledge was at the time. So could you share a bit, how it emerged, how you even came to the idea, what were the key points in coming up with such a model?
You're right. Yeah. So at that time, I think the consensus was clearly that the basal forebrain or the basal ganglia were structures. This, and maybe the best would to say Kemp and Powell's 71 paper sort of summarizes the thinking better than any. His view was that the basal ganglia are the mechanism whereby different cortical areas can initiate movement. So it's an action selection. I think you used that word actually.
Yeah.
But what the notion was that different cortical areas could initiate movement via the basal ganglia and thalamus, with that output going directly to the motor cortex. And, there was also some sense that it was going to the medial areas as well, SMA. But that was, I would say, so accepted that, well, how did we come to the different view? The work at the NIH, what we found was that the neurons related to body parts and movement were in a very circumscribed area, somatotopically organized, and that the specificity was maintained throughout. That's a point that sometimes is not clear. What we found that neurons in the putamen, motor areas of the putamen, somatotopically organized, in the external pallidum, somatotopically organized, ditto GPI, that they were at each level, the specificity for movement was preserved as far as we could tell. Very little driving from any movement of any other part. There were associated movements, but that was a separate issue. So we saw that the organization was one that was functionally specific. First, there was an arm, leg, motor area, face as well, and these were all separate, but focusing narrowing into smaller and smaller numbers of cells at each jump. I mean, a remarkable reduction, of course, from cortex through striatum putamen and on down to the output. So, and then what we found at the same time was that the cells outside the motor areas of those were not specifically related to movement in any obvious way. Not that they were not related, but not in the somatotopic pattern. And then a lot of anatomy began to show, that the projections to the striatum were, well, we knew the projections to the striatum were topographic, if you will. And then the question was, how did it proceed from there was the real issue. So we had a strong hunch and believe that the outside, that the non-motor areas were receiving input in a similar manner, that is topographic, and that was maintained throughout the network. That was the essence of it. This view was interesting because, this idea came to us pretty clearly, and Apostolos Georgopoulos and I were working together, and that time, this is by total coincidence, Tom Powell, the person who co-author or the major writer of the summary, was visiting Vernon Mountcastle's lab for the year. And we began to talk to him about this, and he kind of sort of went, no, guys, sorry. This is not the way it is. Very nicely. But so we propose that we meet on a regular basis, week after week after week, until he would agree or not agree, disagree. Well, after about a month, he began to accept everything we were kind of proposing and was fully behind it. It was a remarkable change. When we put this thing together, I sent it to various people. Nobody liked it, really. Or not, no, I don't want to say that. Some people did not like it, thought it, this, I don't know what. Ed Everts never replied to me.
Okay.
He never commented. So, but anyway.
Were you in Mountcastle's lab at the time, or were you already a PI there?
Yeah. Mountcastle had space, is how I happened to be there for a couple of years, and then we went over with new space at the City Hospital.
And maybe just to clarify, I think Thomas Powell was the leading anatomist in the field. He was from Wales, right? And he, in the beginning, did not believe you, but then apparently, after many discussions, came across, which is amazing. Were there other key roadblocks or like challenges or breakthroughs that had to happen until the model became established?
Well, it didn't. I didn't feel that it lasted for long. I didn't hear much in the way of, after it was published, I think people generally accepted it. And the data, the studies just seemed to go further and further in supporting it.
Great. So one key thing in the original model was that it proposes a partially closed loop, right? Projecting, so the thalamus, so cortex projects to striatum, then pallidum, substantia nigra, back to the thalamus, which would then project only to one of the regions that originally.
Yes, that's right. That's right.
Is that still true? Like, would you still think?
I think it's probably maybe partly true. I don't know the answer.
Yeah. Okay.
But the original one was because that's what the data was kind of pointing in that time. But I think since the projection to the motor cortex and the different cortical areas, I think that has become clearer and clearer.
Great. So maybe in that regard, I'm a big fan of Larry Swanson's extension of the concept striatum and pallidum. I think Swanson would argue that this, you can, all of the deep nuclei, you could divide them into either being a striatum or a pallidum, essentially, having the function to inhibit or disinhibit other cortical areas. So I think he proposed that you could, essentially replicate your model across other regions that are not formally striatum and pallidum. What do you think about that?
I don't have any strong reaction.
Sure.
I really don't. I think
Gotcha.
it's very interesting concept. Yeah.
I think the model right now is often referred to as the Mahlon DeLong model, right? In brief, and I think it builds on two papers. At least that's the main conception in the field. The first one being from Albin, Young, and Penny in 1989, researchers at Ann Arbor, and then your DeLong 1990 paper from Johns Hopkins. Together, they are cited 10,000 times. So where many know about the model, maybe few people know how it emerged. So how maybe was there communication between Ann Arbor and so the team at Ann Arbor and yours, or did you exchange ideas, or was it more similar ideas at the same time?
Well, I think our focus was on the somatotopic organization and the motor and the separation.
Yeah.
They were focused on motor. It seemed to me heavily, and most of it was rodent. It was rodent. So.
Gotcha. Right. So and then what I found really interesting, when trying to understand your models as a student, is that the models are functional models, right? So the direct and indirect pathway are really functional pathways of which areas communicate with each other. And it's not really an anatomical model. And I found it then really interesting to see that, the anatomy was I think, quite well understood way before your model, maybe as early as the 1920s by the Vogts, or also clinical work by Ottfried Förster, building on top of them back in the day. But your model is a functional one, and that was the breakthrough. Is that correct? So that, we suddenly understood not just what was wired together, but how these, net activities could shape each other and then lead to deficits in movement disorders and psychiatric diseases.
I've always thought about it. It's interesting. I've always thought about it as a functional anatomic model.
Yeah.
Because the anatomy and the physiology were so important in understanding the detailed organization within the motor circuit. So it's interesting to say that. Clearly it's functional. But and it's not anatomical in the classic sense, but it's physiologic anatomic.
Absolutely. So this is really great. So I think one other key paper, maybe the key paper, was the Alexander DeLong strict paper, where, as you mentioned before, that was built, I think, on top of the paper between you and Georgopoulos in 1981, which showed the parallel organization of these functionally segregated circuits. So, and I think it's still, there are these two concepts. One is being the funnel, where the basal ganglia compresses information to some degree, right? We have less cells in the SDN than in the cortex. But then, of course, also the parallel circuits.
Right.
And probably both concepts are true to some degree, right? There is some sort of integration and compression, but it's still also very important that the segregation is retained. So I find that really crucial and important to learn about the brain. How much is being integrated, from different areas in the cortex, but how much is also being segregated?
Yeah, no, I think I agree with you. That's probably one of the most difficult and interesting issues in this whole business. There's so much. There's the fact that the dendritic tree of the pallidal neurons is flayed out like a stick on me, do something to me. I mean, it's a very dense layer of the arbor, dendritic arbor of the GP neurons. And so they want to collect a lot of information from a large area. We're here, sort of, and yet the recordings point very much to specificity. And I mentioned the microexcitable. I don't know if I want me to say a word about that or not, but there are zones in the striatum that are microexcitable at very low intensity through the microelectrode that are the neurons recorded in that zones are totally congruent, or not totally, but almost always highly congruent with the movement. If it's a wrist movement, you will find neurons in that microexcitable zone that are just all related to passive or active wrist movement. So it's that segregation of function seems so, and it's present at every level we've looked. In the pallidum, and we did in Japan, we did a lot of work with the group there, exploring very close penetrations in the pallidum. So, but the issue is not so much how much congruence is there within the motor circuit, but to what degree do these outside circuits, the cognitive, associative, limbic, play a role? Are they able to influence? And many of, I know there's some evidence now that SDN neurons can have input from two different cortical areas or some influences, but I haven't seen a lot of the work says there's a diffuse dusting of terminals, but doesn't show that they actually connect. So the physiology is not there. It's an open question. I think.
Yeah, I also think a lot of insight is in exactly that maybe question, because I also learned from Hagai Bergman's book that I recently read that the DPI neurons are really orthogonal to each other often, right? They don't share much information. So even though you're right, they stretch out and condense a lot.
Yeah, let me tell you. So I not said, but one of the most remarkable things, and years and years of recording at NIH and Hopkins and all that, I don't think I ever saw two neurons that were correlated next to, when you could record two neurons, they were always doing different things.
In the GPI?
In GPI, yeah.
Yeah.
GPI, doesn't matter.
Okay.
Yep.
That is so fascinating. So I think it's a good time to play one question I recorded, or a guest recorded, which is Marwan Hariz. Let me see. So this is the first question by Marwan Hariz.
Dear Mahlon, I am so honored to have been asked to participate in this interview and to be given the honor to ask few questions. I have 3 questions. This is the first one. Given that the 2 main output structures of the basal ganglia are the GPI and the SNR, how do you explain that it is only the GPI that is a valid, efficient target for lesions or DBS in Parkinson's disease, while DBS on the SNR does not seem to work? Thank you for your answer.
It's an interesting question. We have mapped the SNR in the primate and found some neurons related to face movement and face and tongue movements, and a little bit some other body parts, but very little, and they're very lateral. So it's like the pars lateral. Well, No, that's the rodent story. No. So there is very little there that is getting input from the striatal motor portions. It is the rest of the nigra is caudal or is associative or limbic or beyond. I don't think they're limbic. Yeah. So it's just that the substrate isn't there. It's mostly all in GPI and in the ANSA. Well, no, yeah, that's a different topic too. Yeah.
Yeah, but that is interesting. So that could mean that potentially the nigra could be a psychiatric target.
Yes. Well, yeah, I think it could be, and it's also the eye movement stuff is there.
Okay.
In the nigra.
Great. So moving on, in the early 1980s, some drug users' bad luck was exactly the opposite for neuroscience and also for your lab. A powder produced in backroom labs and sold on the street as a new synthetic heroin sometimes became contaminated by a close chemical cousin, leading to what the press called frozen addicts. Can you tell us a bit about that time?
Okay, so the question you asked me earlier on about key people, I was going to extend it to key animals or key models, and by all means, the introduction of the MPTP treated primate was a door opened to understanding, I think, the basal ganglia and Parkinson's disease. And when we saw that, we just shifted immediately to begin studying that. As I said, I was always interested in the basal ganglia, and I was going down that independently, but that was a hard turn to Parkinson's, and it's interesting little tidbits and just the reaction of different people. When I told Vernon what we were doing, he just shook his head. He said, "No, don't do it. You won't find anything."
Oh wow!
And yeah, so I said, "Well, Vern, we're doing it now. We're starting." I'll never forget the first day. I should have thought of this before as a eureka moment, because the first day, Bill Miller was a graduate student who had started in the lab, and I said, "Look, this is your your chance, your job, your life, a little chance of a lifetime, and he did a bang up job on the whole thing. It's just super. But anyway, the first day we recorded, we stuck the electrode through the striatum. As you go through the striatum, you don't really find very much. There are a few cells that are active, but it's a very quiet place. And I had already, believe this is the rest of the story, I had already done this when I was at the NIH with drugs to create Parkinson's disease. I thought the striatum would just light up, would be on fire, zero. And I never had the sense to go deeper. I don't ask, that was a strange thing, but we were so convinced that the striatum would light up if there was going to be anything. But anyway, neither with MPTP nor the other agents to create Parkinson's did we see any striatal change. And that's true in most animals. So it's really much more in but in the external pallidum, it was immediately obvious. And as we went on down into GPI, it was crystal clear. First track.
That was a eureka moment, you'd say, because of the
oh yeah,
yeah.
And I'd forgotten about that until just start talking here. Yeah.
Sure. So great. So and then in the old days, subthalamotomy. So if surgeons did a subthalamotomy, that did not mean they would lesion the subthalamic nucleus, but lesioning below the thalamus, because in fact, people shied away from lesioning the STN out of fear of hematopolism. But then your paper with Hagai Bergman in 1990 in Science changed that. Can you tell us that story?
Yeah, that's that was clearly one of the biggest findings, the most important in a way.
Yeah.
But and I agree. The subthalamotomies had been done. Were not really subthalamic nucleus, what they talked about that area. I was almost 100% convinced that it would work. Why wouldn't it? And there was I think a general consensus from all of the available evidence that showing that the output was excitatory from GPE. That was a big finding, and that the 2DG studies clearly showed that the changes were as predicted, would be consistent with that overactivity in the STN. So shutting it down ought to make it better. So I was very pleased and excited. Hagai was very, very excited, and I think everybody was amazed when it happened. But I didn't have I wasn't surprised. I felt okay. that makes sense.
But isn't that amazing? I mean, maybe for the listeners, we should clarify that a bit further, that, this was really a prediction from the model, right? Obviously, that you and the Albin group and our group both showed that, the Parkinsonian state should lead to overactivity in the STN. So, and that would then obviously lead to, overactivity of TPI, and then, inhibition of the thalamus and less movement. So it was almost theoretical neuroscience prediction from a model. And then, it's a bit like general relativity theory predicted black holes, and then really seeing them is a different thing, right? So maybe just to clarify that a bit further, like how it felt like to then, even though you were not surprised, I'm sure it was still.
Yeah, that's maybe playing it too. I was more pleased than surprised.
Yeah.
And I have to mention the work that others had done on that. With Filion had recorded, and Michel Filion had recorded, and not in MPTP monkeys, but he recorded, and we saw the similar findings in that. And Alan Crossman, working with 2DG, had done beautiful studies confirming what we suspected. So I think the ground. I don't know how many people were really surprised, but I think the people who were thinking and knowledgeable about this probably weren't surprised, but maybe glad.
And then for Hagai Bergman, that was likely his breakthrough. And he told me, he was on the podcast before as well. And he told me he was kind of late to science. So he wasn't very young at the time, right? He came to Emory when he was already, had been in research for a while in Israel as well. Is that correct?
Oh yeah, he came well trained and ready to go. I mean, most of the people I've worked with have just been tremendously, wonderful people, well trained. But Hagai, did Hagai say he was surprised, or he?
No, I don't remember whether we talked about surprise or not.
Yeah. Well, it was obviously very important and sort of check the box kind of.
And I mean, if we stop, like if we just think for the next then 5 years or so, then as everybody knows, Grenoble did something tremendous with the STN DBS, right? Patricia Lindesian was also on the podcast, and Pierre Polak was on the podcast. And in a way, I asked that question to Hagai as well. You obviously paved the way to deep brain stimulation, and with that, you SDN-DBS, I mean, and with that you paved the way to helping thousands of people worldwide that have received deep brain stimulation so far. So how does that feel? Like, let's say maybe you have some friends even with deep brain stimulation, or some people that you know. How does it feel to know that this builds on top of your breakthrough?
Oh, I think the translation of this to the treating diseases has just been the most amazing thing. I can honestly say, when I went to the NIH to study the basal ganglia, I had no intent of curing any disease. I didn't know what disease to even cure. I was purely interested in the neuroscience, and it was only after I went to Hopkins that, in the clinical environment, I think, and in the rapid, development of the model, is when, and then the experience. So, but we had not done anything with that. I'm a little bit ahead of the story, but I felt that DBS, when it was introduced, was really a breakthrough of enormous magnitude. But we had, because of the concern about lesioning the subthalamic nucleus, we had said, no, but we've got to do something. But that's a little bit later story. So that's when we went to pallidotomy, and we spent a good amount of effort in. But that's a next layer, I guess.
So that was with Jerry Vitek, right? That then to establish pallidotomy and trials.
So Jerry and a whole large group of us moved en masse to Emory. That was the so-called hemorrhage to Emory. And that was, it was just the movement disorder part of the department that went. But that's when we began preparing for surgery. But we've been doing surgery at Hopkins with Hank Nauta, son, Wally Nauta's son, Hank, and Fred Lenz. We had recruited Fred Lenz to come. So we were starting to do, and we were doing thalamotomies, but had not gone beyond that. I was just saying, my interest in contact with surgeons while I was at the NIH and at Hopkins was, I think my greatest contact was Narabayashi in Japan. I spent a lot of time in Japan with Narabayashi, the sort of world famous psychosurgeon. He was a psychiatrist, actually. But so the idea of doing surgery was very much on my mind.
Yeah.
But what kind was a separate issue. Yeah.
Maybe before we get into that, I think it's good to play another question by Marwan, which fits perfectly at this point, shall we?
Sure.
My second question is, we know that the STN as a surgical target for Parkinson's disease is a discovery by Hagai, Bergman, and yourself. And the STN is considered the most favored and efficient target for DBS in the whole world, except maybe in the United States, where many still insist that DBS in either GPI or STN give equal results. How do you explain this discrepancy? Thank you.
Well, that is a wonderful question. We are guilty of all of that. Our experience with pallidotomy was so positive that we felt it was important to try it and explore it. And others had done it previously. It wasn't a brand new stuff. But we found we had very good results with parallel DBS. And we did, the most important thing is that we did careful mapping, microelectrode mapping of the motor area. So we could place our electrode in the right spot. I mean, all of this is basic to anybody who does this kind of stuff, but the microelectrode mapping was very important, both in our lesioning and for our recording, or for our stimulation. And so we felt quite comfortable with it. And I honestly think the results are fairly similar. We do separate people with cognitive or any other problems. We will do GPI. I think GPI, the motor area in GPI is quite a bit large. It's greatly larger than an STN. So you can hit the motor network, motor circuit, without spilling into overlapping or nearby cognitive or associative limbic, not limbic so much as the cognitive. So, and I think the studies are pretty comparable in terms of outcome. And I think we do select patients. Young patient, we would do STN. Tremor, we do STN probably. But GPI is very effective for tremor. It may take a little longer interestingly, to manifest, but we found all kinds of tremor-related cells and with lesion, but it can be delayed. That's the curious thing about it.
Yeah, it's very, very interesting.
I suspect we have poisoned the water because early on, I think we were doing this quite a lot.
Okay, I hope Marwan is happy with that answer. So because I also myself I've worked in Berlin and then now here in Boston, and I wouldn't even think I see such a big difference in the choices of how DBS is done. It's still at least between these two centers. Still, I think I would say in both centers, STN is usually for most cases the default, but then there are sometimes cases with more dyskinesias or so where or other issues where then GPI is favored with great results as well. But it's certainly a very interesting question also to me why both work so well, right? So it that already suggests obviously that it's a network effect. It's not. So I think we can play another question this time by Hagai Bergman because we talked about him. But that question will lead us to maybe a slightly different topic, a slight detour. And I might just for the readers also say a bit about that. So it's about GPE neurons. And Hagai, in his book, writes about recordings in the GPE neurons that show particular pauses that I think you know very well, but not so many people might know that are not doing electrophysiology in the basal ganglia, because I think they still remain a big mystery. So there have been some, apparently there were some relationships to, for example, arousal level. So apparently the pauses will be less frequent and shorter when the monkey is engaged in a behavioral task. But there's no clear, so according to Hagai, there's no clear reason yet for or we don't know what these pauses signify. And I think that's exactly what Hagai wants to know. So let's, from you. So I'll play that question now.
Hi Mahlon, long time no see, I miss you. Andy was kind enough to ask me to pose a question to you. So I'll follow my Middle Eastern style, don't change over 30 years, and I will ask two questions. My first question is if you remember the first time you noticed the spontaneous process of the GPE high-frequency discharge neuron. What was your thinking at that time? Have you been thinking that this is artifact, or you recognize it as a very strong feature of this neuron? And second question is now, 50 years later, What do you think is the role of this process? Thank you so much, Mahlon. I am looking forward to hear this podcast. Hagai.
Okay. Well, that is an embarrassing question because I have no idea and of what those could be. We noticed them, prominent findings, and I never could make any sense out of it. But we never tried. I never tried to think about them or look at them in different conditions. I think I've seen them become longer with periods of rest or quiet, maybe relaxation. But I don't think we once looked at the basal ganglia in sleep. There's a lot of recordings during sleep, and never published it, believe it or not, but never saw any correlation that I can recall or any specific changes. Everything got slower. Everything got slower during sleep. So after 50 years, I haven't learned a thing. No.
Okay, great. But I think according at least to Hagai's book, he would say the same. So it still remains one of the big mysteries according to the book. So yet to be discovered by a new generation. So maybe thinking in a similar line of Hagai's question, if you look back 50 years later, now what of your model do you think still holds true today? Or which crucial things would you adjust or add? Or
well, I think I mentioned a couple of things that I mean. There's a lot. There will be a lot of further modification of the model. I have no doubt. And to what extent these zones remain segregated, and to what extent there's crosstalk or modulation from not other cortical areas, I think is still up for grabs. And but I mentioned these striatal microexcitable zones, which to me were just further evidence for the fine grain specificity of organization of these motor networks. It is one of the most remarkable things. I know that others have picked it up and tried to do something with it a little bit, but nothing seems to have come out. But I think they're equivalent to the cortical microexcitable zones. There must be. We lesioned the GPI and could not evoke, or not GPI, but the striatum could not evoke responses. So I think they're activating output elements.
And then a decade after your work and your model, the Redgrave, Gurney, and Prescott model originated, which became popular in the computational modeling domain. How would you say the two models were different? So what was added in the Redgrave Gurney model, and what was similar?
Well, I was going to. I think we had talked about that briefly, but I was going to ask you what I'm not as familiar, or I can't be as incisive, perhaps, as you would be, and specific. What specifically were you seeing?
So I don't. So it's exactly the point that to me these models look very, very similar, but yours was 10 years before. So I thought maybe what has changed between them. I think one key point that I've understood with the Redgrave model was that it was a computational model where they really implemented, simulated, let's say, the computer code, right? So and maybe that was the key addition. But I just thought maybe you had been in contact with them or so.
No, not really. Well, we did talk about, we've published together and done other things, but have never had this conversation. So I'm not very enlightening on that.
So while the model was crucial in advancing our knowledge in movement disorders, you also mentioned that it was a godsend for psychiatry. And I was talking very briefly via email with Helen Mayberg before this about the upcoming podcast with you, and she also mentioned that you were increasingly interested in depression. So do you want to share some thoughts in that direction of psychiatric?
Oh boy, yeah. It's I'm very interested in I almost went into psychiatry to just fill in the gaps. Yeah. I was 50-50 when I left Hopkins or when I left NIH, and the department at Hopkins was still it was starting to be biological, but it was still not, and I knew where neurology was going. So I got on that train and stayed on it. And that I had never had any second thoughts, but my interests, I think, are still in many ways highly pushed towards that psychiatric psychopathology kind of issues. And I've been really very stimulated by learning more about something I should have learned about a long time ago, which is the effect of psychoactive drugs. The LSD, and what's happening in psychiatry. My remarkable effects of that drug that seem to set a different. With Helen Mayberg, Helen has this idea that something is set and can't be. You got to get out of that set. And that seems exactly what these drugs do, is to take people out of their set and expose them to a far greater world, a far more beautiful, integrated, place that they come back from. They have this transcendental experience. Yeah. I'm talking about the real cases, where they really do take the trip, and they come back altered in ways that are unbelievable and in a lasting way. And so it's the drug that precipitates the experience, but it's the experience that seems to have the lasting effect. It's not a drug effect, and there's no drug addiction or craving. So that to me was like, oh my God, how did I miss that? And Ed Everts, who I worked with, at NIH, he was in the midst of that. He was a psychiatrist who was very much involved in all of that with Leary and the whole debacle.
Definitely, and that's very interesting. So I'd be more than happy to hear a bit more about that. Like when you said these were like real effects, did you see patients, or have you seen like cases of treatment now that it's becoming more popular again, or?
It's all being done under very strict protocols. There's always a person with the patient who helps. You may need somebody to make in the right setting and can support and all of that. And I've talked with the psychiatrist, and I've talked with our chair, and my idea was, somebody will take it, but that's fine, that this should be used for patients, not only those with terminal cancer, but maybe those with chronic debilitating diseases like Parkinson's and other disorders. That if you could really safely take people out of their world, and into something more glorious and unified and wonderful, and let them come back with that. Why not?
I couldn't agree more. So one very remarkable, you mentioned it's safe, a remarkable thing about LSD is that you essentially can't overdose it, right? And that doesn't apply even to aspirin, right? There's hardly something that you could, in theory, take with a very high dose, and the only, I think, real danger with an LSD trip would be maybe that, if you already have a heart failure, that, you get too excited and then could die out of heart failure. But that's the only real thing that could happen. So there are not many even drugs that are like medicine drugs that are as safe as these hallucinogens. So and I find it very fascinating as well. So taking people out of the maybe high entropy, low entropy state where they are locked in their let's say small world. I had not thought about Parkinson's with it, so that's really interesting. But definitely in depression.
Yeah, I don't think it would help their Parkinson's, but
sure.
But if just the positive outcome, it would be, you just have to try.
Yeah.
And it's a whole spectrum of drugs. All starting with LSD.
Yeah.
Psilocybin on down.
Psilocybin and ayahuasca.
Magic mushroom.
Yeah. Yeah, absolutely. And you're right, maybe also for the listeners, so these trips that are done medically now, I think at various institutions, including also Johns Hopkins, are often 5 times the doses of what is done on the street, right? So it's a full-on trip, that the real tunnel
Yeah, Michael Pollan's book was what turned me on to this, his fairly recent book.
Interesting. Same for me. How to Change Your Mind. I love the book.
It's a remarkable book. I'm pushing it on everybody.
Same for me. I bought some copies, sent it to people. I totally agree. It's a great overview. Yeah, very interesting. So then one maybe last topic that you focused on in your early years of research at Johns Hopkins was the nucleus basalis, and you found support for the cholinergic hypothesis in Alzheimer's disease. Could you tell us a bit about that?
Yes. Okay. That's a fun story. So I was thinking about, people who have influenced your life. Who are they? Places you've been, where are they, environmental, money, all kinds of things come into interesting and important events. But one of the, I came to this recently and thinking, what was great about the NIH, and all of us who were at the NIH at that time, Mark Hallett was there, Tom Thatch, Bob Works. A lot of them were oculomotor physiologists, but a lot of physiologists, and just a roster of future Nobel Prize laureates, whatever, were there. But we had a journal club that met every week, and we'd go to everybody's house, rotate, and we had the most wonderful discussions you can ever imagine. I think all of us, and every time we get together, it's one of our recurrent thoughts. What a wonderful world it was, both physically and intellectually stimulating, and remarkable, wonderful group of people. And so why am I telling you this? Oh, okay, yeah. So the next thing I thought about, the other situational environmental thing that had a tremendous idea, and it gave birth to me, where to look for the cholinergic deficit in Alzheimer's. I had done work with these basal forebrain neurons. We had recorded from them because they were in the way. We were trying to record fallible activity, and there they are scattered all through the lamina and below. And so we had to describe and separate these out, wheat from the chaff. But we knew they were cholinergic. That was well known. Meselman had shown that, and others. And I was out at the primate center, and we had discussions about them. But nothing ever really clicked until I realized that the cholinergic deficit could be from the loss of these cells. And so we studied, we started looking at Alzheimer patient brain, and that's what we found. And so it didn't, the cholinergic hypothesis was well established. That was a part of the thinking, but people were not clear about how it came about. And sure enough, it was the first time. It was like recording in the MPTP monkey the first first brain we looked at, they were wiped out. And of course, Lewy bodies were found initially and still in these cells. So that's the story of that.
Very nice.
But it came out of discussion in this carpool we had with Dave Z, and Bob Works and the usual crew that we were.
Great. That's a wonderful story to share. That these discussions led to these discoveries. It's always, crowd wisdom, picking other people's brains. We young people should do that more as well. I think the world has become so fast. I was really envying you when you mentioned about these journal pubs. So that sounds really great. So another thing that you already mentioned a bit that had then also received less attention in your body of work is the presence of these striatal microexcitable zones. You called them SMZs, and you already mentioned them quite a bit, but can you talk a bit more about what they are?
So Gary Alexander was the key person in this, and Gary was really a wonderful physiologist. And what he found was in recording from the motor regions that there were, and it was kind of not an afterthought, but it was add-on after mapping out and looking at these areas in the putamen, rather great detail, that showed that stimulation, evoked movements at very low threshold. This is micro stimulation, and we were so puzzled, and that I think they would anywhere from 5 millimeters to from 1 to 5 millimeters, 1 to 1.5 millimeters in length. Or they some could be short, some longer than others, but they were definitely zones, and virtually all the neurons in that zone were related to the movement evoked at threshold. So we never went above threshold. Once you go above threshold, then you start getting other movements. So it's not to say that but the basic building block seemed to be these little tiny zones, and we could only imagine that they came somehow by this very topographic projection from the motor cortex, from the motor cortex microexcitable zones. A number of people have talked about it, and I don't know, even anatomically, I don't know, maybe there's something to be said.
The bundles from the striatopallidofugal bundle in the striatum, if you look at that, right, the Wilson's pencils, they are also these thin zones that would obviously have a lot of white matter. Then the other thing that came to mind would be the striosomes that also are these patches in the striatum. Any chance that could be linked up, like your SMZs, would they coincide with either Wilson's pencils or striosomes? Do you know? No,
they would not. The pencils are downstream and are right there in GP. And so all of this is up in the putamen. It's in the receiving area.
But
But you have these pencils in the striatum, right? You have the same, like they.
Do they start in the striatum? I had. That's it. Well, you know more than I do, because I always just sort of thought they were bundled. Well, but those would be so big. Those pencils would be so big. I think they would. But I'll have to look at. Yeah. I'll talk to you, Yolande Smith. Yolande. I confess ignorance about any of that. So it was known that these take origin in the putamen or in the striatum. Huh.
At least maybe we can discuss offline. So I'm also, it's obviously also not my strong suit, but I'm pretty sure that you have these streaks in the putamen as well.
Right.
Let's maybe wrap up with some rapid fire questions, more like general questions before I let you go. Thank you so much. I'm stealing so much of your valuable time. And maybe the first one could be the Marwan Hariz's last question, which is a very general one, I think. So I'll play that.
I have the last question here. So, in your opinion, as a movement disorder neurologist, what is the difference between a neurosurgeon implanting DBS leads in the brain in order for the neurologist to deliver electricity to the patient, on one hand, and on the other hand, a general surgeon implanting a catheter in the duodenum in order for the neurologist to deliver duodopa to the patient? What's the difference between these two, according to you? Thank you.
Well, I think it's a lot easier to put the catheter in the duodenum into the right part of the brain, getting the electrode in the right spot. And I wanted to say one thing, or maybe two, about the neurosurgeons. I was going to add Roy McKay's name to the people who have made a huge difference and done wonders in a sense. When we came to Emory, we were leaving, an environment, a neurosurgical environment we had sort of established with Fred Lenz and others, and Nauta, who had been there. But we knew there was a neurosurgeon at Emory, but we didn't know much about Roy. And Jerry and I'll never forget our first meeting. We were so amazed how interested and eager he was to join us. And we did know that he was very interested in research, and he had already done some really very important work in adrenal and other things were going on and protection. So Roy, I think, played such a critical, important role in our early ventures into the brain. It was a member of the team. I mean, we were there all together, and Roy was involved in every aspect. And he was a meticulous surgeon, having worked with a number of surgeons and seen other people. I spent time with Strickler, and I had been with Narabayashi. I sort of had a good feel for how people operated. So it was a wonderful discovery about Roy. And so I'll never forget the day we did our first pallidotomy. And this is coming after the STN lesion and all that, when we didn't want to. We had made an investment in that. We had a lot of NIH support to do it. But we were up until 2 a.m. with that first patient. And the first patient was absolutely scary in a way. It was a fairly young man with Parkinson's. He had definite Parkinson's, but was largely unilateral and had tremor. And he wanted to be the first patient to ever to have this experience, lesion. We told him, and we thought, well, that'll dissuade him. That made him determined. And so we thought, well, he shakes out every way we could test him on everything. He was the real thing. So we did it, and the mapping went well, but we were very careful and we used our mapping to place the lesion, and it was a tremendous success. It was just incredible, the benefit. I'll never forget that night. All that happened, and so Roy left us later, 10 years later or so, but went on to better things, and but he was a tremendous contribution, and the importance of neurosurgeon, who for neurology is to find a neurosurgeon who will take the time and can work and understands exactly what you're doing, and it was a tremendous asset.
Great. So again, wrapping up, just some very general questions. What do you think the future of the field of neuromodulation will look like? What are the big next things that are coming up?
Well, all of the technological, quote, closed loop, all of the technological advances are so remarkable. I think it's going to get, this is a no-brainer. It's going to get better, easier. There is a long-term commitment. The thing that bothers me about deep brain stimulation is the patient. We did after pallidotomies in the pilot. We did many pallidotomies. Highly successful, very effective. I should make this point clear. I still carry this bias. I think this should be considered in patients, but there may be better ways of doing this now, with the focused ultrasound and whatnot.
Yeah,
that this can be done. But the effects of pallidotomy are remarkable and lasting. I followed the first patient I mentioned, the first patient we had. I followed him until he died, maybe 10 years ago. And he was absolutely rock solid. The motility in that arm was just incredible. Well, I was thinking of how we were, patients who had a pallidotomy was diagnose, treat, and adios, almost, to extend that a little bit. Not really, but you'd see them back in 6 months or whatever. And they were free, and they were able to navigate. Now you have a umbilical cord to sort of, to some extent, with the patients with DBS, they're coming back. So the more independent that becomes of you or a programmer, the better. I think everything should work in that direction so that this can program itself and turn itself on at the right times and pick the best settings and do all the heavy lifting without all of the commitment ties.
That's a great point.
I would also argue that, I think I said it, that I think there might be indeed a place for when pallidotomy has gone in and out so many times in the history of functional surgery. I mean, it was abandoned prematurely, of course. When
levodopa came.
Oh, can I just say one thing about pallidotomy? Is Absolutely. You've got to put it in the right spot. It's a no-brainer. But what we found is that the classic target isn't the right target, and that's what Svensson demonstrated in that much neglected and underappreciated article. He showed that the real target was more posterolateral, or however you describe it. It was not central as people were using it. Even when I was with Narabayashi, he was using a central target, and I could not persuade him, even though we were best of friends. At least I didn't see him nudging back. He had done it for so long.
We did not know that it was started central. Now with DBS being posterolateral, it's so obvious too, because that's the motor domain, right? But I didn't know
And
that.
that's where we found it. You know, we went where we found it. There was so we did often 3, 4, 5 tracks, depending how many we needed to be sure we got it in the right spot.
And you did test stimulate them before you lesioned?
Yeah.
Okay. Yeah, great. Because maybe that is one big misconception in the field nowadays, that people think, you know, that's what the Grenoble team came up with, that they had test stimulation and then the tremor already stopped. But I think everybody knew that at the time.
You know,
right?
we didn't always do test stimulation. I don't want to say that, but what we did was we knew the boundaries, and we often made 3 lesions, 2 lateral and 1 more in between, more medial. So we were careful to get the complete motor map as complete as we could be. The biggest problem with pallidotomy was that you made the lesion too small. Often the patients that we saw who'd had surgeries done with a single lesion, and even in our own case, when we didn't make it large enough, the results would fade.
Great. I mean, I think the FDA approval for focused ultrasound pallidotomy is really pending or coming soon. So might be that there's a real renaissance again of pallidotomies in the future. So are there missed opportunities? I mean, pallidotomy is maybe one of them, but are there missed opportunities that you can think of? Things we should be doing but are not doing as a field?
I guess the issue is beyond motor into the cognitive, emotional pieces. I think those are the wide open areas, you know, with a lot of controversy and uncertainty. But I know, talking with Helen, that can really work, and the newer work seems to work. I mean, so progress, but I think that's where I would be if I were doing anything now. I'm gonna stick to drugs.
Sounds great. And then maybe last question, any advice for young researchers that are entering the field of neuromodulation? Any tips or tricks?
Well, I think what's happened, it's pretty obvious, is that people with engineering capability should find they're a happy home, and you know, it can be extremely valuable. I think. I mean, we have Cameron, of course, is the role model that I have. And Cameron was with us for a number of years, and Jerry worked closely.
We did a fellowship with you, right, at Emory to learn movement disorders and so on. Is that true?
Yeah, he was a fellow. Yeah, that's right. So yeah, but that's picking out a particular type of person. I think, you know, you've got to follow what you really want, what you enjoy, what you want, but there has to be an opportunity. There has to be resources. There has to be an environment that will be supportive and not get in the way. You know, but I think, you know, if you're not emotionally involved, it's not going to work. It's a passion.
Thank you so much. Anything we have not covered, but that you would like to? I know this was long, but do you have anything else you would like to share?
Oh my! I think we've probably covered most of.
Yeah, I've occupied you long enough, I think. So thank you so much for this. This was really exciting for me to be able to talk with you.
This was fun. I think what you're doing is really a wonderful thing, and I'll have to listen to some more of the podcasts. I just listened to a couple of them, but it's a great opportunity, I think, to bring people together in COVID times, in a sense, I mean, or to share some of but also people who have lived through difficult and other times.
Super. I totally agree. For me, it's a great way to learn as well, and really to hear a bit about things I haven't lived myself. So this is really amazing. Thank you so much.
Thank you. Thank you, Andy. Yeah.